Hey guys, in this tutorial we talk about random numbers in NumPy. So let's start. What is a random number? Random number doesn't mean a different number every time. Random means sometimes something that cannot be predicate logically. Pseudo random and true random. Computers work on programs, and programs are definitive set of instructions, so it means there must be some algorithm to generate a random numbers as well. If there is a program to generate random number, it can be predicate. Thus, it is not truly random. Random numbers generated thought a generation algorithm are called pseudo-random. Can we make truly random numbers? Yes. In order to generate a truly random number on our computer, we need to get the random data from some outside source. This outside source is generally our keystroke, mouse movements, data on network, and etc. We don't need truly random numbers unless it's related to security or the basis of application is the randomness. In this tutorial we will be using pseudo-random numbers. So generate random number. NumPy offers a random module to work with random numbers. So import NumPy as np and x is random. X is from NumPy. From NumPy import random and random dot rand int and 100 print x, save and run, and we have 99. Run again, we have 3, and run again, we have 95. And generate a random integer from 0 to 100 and generate random float. The random modules rand method returns the random float between 1 and 0 and 1. So copy and paste and rand method, remove this, run, we have this number, run again, we have this number, and and generate random array. In NumPy we work with arrays, and you can use the two methods from these examples to make random arrays. The randomness method takes a size parameter where you can specify the shape of an array. So generate a 1D array containing 5 random integers from 0 to 100. X, copy and paste, x is random dot randint and 100, and size is 5. Run, and we have this array. Run again, and we have this array. Or generate a 2D array with 3 rows, each row containing random integers from 0 to 100. So in here, size 3, 3 rows and 5 columns. Run, and we have this array. Run again, and and floats. The run method also allows you to specify the shape of the array. For example, rand and set the size 5. Generate a 1D array containing 5 random floats, and we have this array. Run again, and this. Or generate a 2D array with 3 rows, each row containing 5 random numbers, 3 and 5. Run, and this array. Or generate random number from array. The choice method allows you to generate a random value based on an array of values. The choice method takes an array as a parameter and randomly returns one of the values. So x is random dot choice and send the array 3, 5, 7 and 9, save and run, and we have 3, run again, we have 9, run again, we have 5, and run again, we have 5. And the choice method also allows you to return an array of values. Add a size parameter to specify the shape of the array. So in here, set size and 3 and 5, run, and generate a 2D array that consists of the values in this array. And we have this array. Run again and run again. Hey guys, in this part we talk about random data distribution. What's data distribution? Data distribution is a list of all possible values and how often each value occurs. Such lists are important when working with statistics and data science. The random module offer methods that returns randomly generated data distribution. Random distribution. A random distribution is a set of random numbers that follow a certain probability density function. Probability density function is a function that describes a continuous probability. We can generate random numbers based on defined probabilities using the choice method of the random module. The choice method allows us to specify the probability for each value. The probability is set by a number between 0 and 1, where 0 means that the value will never occur and 1 means that the value will always occur. So, for example, generate a 1D array containing 100 values where each value has to be 3, 5, 7 or 9. So x is random dot choice and values is 3, 5, 7 and 9, and probabilities are 0.3, 0.6 and 0.0. So the probability for the value to be 3 is set to be 0.1, 5 is 0.3, 7 is 0.6 and 9 is 0. So print x, x and run. What's wrong? Yeah. I'm sorry, set the size and size is 100. I'm sorry, and run. And we have this array 7, 7, 5, and we don't have 0. We don't have 9. And the sum of all probability numbers should be 1. Even if you run this example above 100 times, the value 9 will never occur. You can return arrays of any shape and size by specifying the shape in the size parameter. For example, return a 2D array with 3 rows, each containing 5 values. So 3 and 5. 3 rows and 5, each containing 5 values. Run again, and we have this 2D array, 5 values and 3 arrays. Hey guys, in this part we talk about random permutations. A permutation refers to an arrangement of elements. For example, this list 3 and 2 and 1 is a permutation of this list 1 and 2 and 3, and vice versa. The NumPy random module provides two methods for this, shuffle and permutation. So from NumPy import random and shuffling arrays. Shuffle means changing arrangement of elements in place. So and import NumPy as MP. So array is mp.array and 5 and random.shuffle array. Print array. Save and run, and we have these results. And the shuffle method makes change to the original array, generating permutation of arrays. So array is mp.array and comment this, print. So array 2 is random dot permutation array, and print array 2 and array 1. Save and run, and we have these values. This is array and this is array 2. And the permutation method returns a rearranged array and leaves the original array unchanged. Hey guys, in this part we talk about normal distribution. Visualize distributions with Seaborn. Seaborn is a library that uses matplotlib underneath to plot graphs. It will be used to visualize random distributions. So install Seaborn. You can install Seaborn by this command: py and -m pip install Seaborn. Click enter and wait to the install Seaborn. And this plot stands for distribution plot. It takes as input an array and plots a curve corresponding to the distribution of points in the array. So download the Seaborn, waiting. And the Seaborn is installed. And matplotlib. You can install matplotlib by this command: py-m pip install and matplotlib. Click, and I have already installed the matplotlib. So use these. And normal distribution. The normal distribution is one of the most important distributions. It fits the probability distribution of many events, for example IQ scores, heartbeat, and etc. Use the random.normal method to get a normal data distribution. It has three parameters: look, and that means where the peak of the bell exists; scale, or how flat the graph distribution should be; and size, the shape of the returned array. So for example, from NumPy import random x is random dot normal, and size is 2 and 3, and print x. Run, and we have this 2D array. And for example, generate a random normal distribution of size 2 times 3 with mean at 1 and a standard deviation of 2. So set look 1 and scale 2. Run, and we have this 2D array. We have 1, and yeah, run again, and we have 4, 3, and yeah. And visualization of normal distribution. So import matplotlib.pyplot as plt, and import seaborn as SNS, and in here comment and SNS dot distplot random dot normal, and size is 100, and hist is false. Run. So sorry, plt dot show. Run, and we have this visualization. So for example, run again, and we have this result. Hey guys, in this part we talk about binomial distribution. Binomial distribution is a discrete distribution. It describes the outcome of binary scenarios. For example, toss of a coin. It will either be head or tails. It has 3 parameters: n as number of torials, p as probability of occurrence of each torial. For example, for toss of a coin, 0.5 each, and size as the shape of the returned array. Discrete distribution is the distribution is defined at separate set of events. For example, coin toss result is a discrete as it can be only head or tails, whereas hay of people is continuous as it can be 170 and 0.1 and so on. So for example, given 10 torials for coin toss generate and 10 data points. So from NumPy import random, and x is random dot binomial, n is 10, p as probability is this, and size is 10. Print x. Run, and we have this. Run again, and run again. And visualization of binomial distribution. Import matplotlib dot pyplot as plt, import seaborn as SNS, and comment SNS dot distplot random dot binomial. So copy this, paste here, and hist is true, and KDE is false. PLT dot show. Run, and we have this visualization, and if I change the size to 100 and run again, we have this. And difference between normal and binomial distribution. The main difference is that normal distribution is continuous, whereas binomial is discrete. But if there are enough data points, it will be quite similar to binomial distribution with certain locand scale. So for example, I add the normal distribution to this visualization, random dot normal and scale is 5 and size is 100. And histogram is false, and histogram to this false, and label to this is normal, and set label binomial. Save and run. And sorry, what's wrong? Hist is false, and remove KDE. And we have this result. So change the n to 100 for better see, and we have this result. For example, run again, and yep. Hey guys, in this part we talk about Poisson distribution. Poisson distribution is a discrete distribution. It estimates how many times an event can be happen in a specified time. For example, if someone eats twice a day, what's probability he will eat thrice? So it has two parameters: lam as rate or non-number of occurrences, for example 2 for above problem; size, the shape of the returned array. So x is random dot Poisson, and lam is 2, size is 10, print x, run, and we have this list. Run again, and run again, and we have these results. And visualization of Poisson distribution. Comment this and comment this. SNS dot distplot random dot Poisson lam 2 and size 1000, and set KDE to false. Run and PLT dot show. Run, and we have this result. For example, run again, and we have this result. And difference between normal and Poisson distribution. Normal distribution is continuous, whereas Poisson is discrete. But we can see that similar to binomial, for a large enough Poisson distribution, it will become similar to normal distribution with certain std_dev and mean. So change lamp to 50, size is 1000, list is false, label is Poisson. Copy and paste random.normal and look is 50 and the scale is 7. List is false and label is normal. Run, and we have this result. For example, run again and we have the same result. And difference between Poisson and binomial distribution. The difference is very subtle. It is that binomial distribution is for discrete terrials, whereas Poisson distribution is for continuous terrials. But for very large n and for very large n and near zero, p binomial distribution is near identical to Poisson distribution, such that n by p is nearly equal to lam. For example, copy and paste, comment, and binomial, and n is 1000 and p is this and size is 1000. Run, and we should have changed 50 to 10 because n by p is nearly equal to lam. Run, and we have this result. If I change to 50, we have this result. Hey guys, in this part we talk about uniform distribution. Uniform distribution used to describe probability where every event has equal chances of occurring. For example, generation of random numbers. It has three parameters. A as lower bound, default is 0, B is upper bound, and default is 1, and size as the shape of the returned array. So from NumPy import random print random dot uniform size is 2 and 3. Run, and we have this result. Run again and run again. And visualization of uniform distribution. So import matplotlib.pyplot as plt, import cburn as sns, and sns.this plot random copy this, paste here, and size is 1000 and east is false. Run. Sorry, dist plot PLT dot show, and we have this result, uniform distribution. Hey guys, in this part we talk about logistic distribution. Logistic distribution is used to describe growth, used extensively in machine learning in logistic regressions or neural networks and etc. It has three parameters: look as where the peak is, default is 0, scale, standard deviation, the flatness of distribution, and default is 0, and size is the shape of the returned array. So draw 2 by 3 samples from a logistic distribution with minat 1 and stddev is 2. So from NumPy import random, import matplotlib for visualization dot pyplot as plt import seaborn as SNS, and print random dot logistic look is 1, scale is 2, size is 2 and 3. Run, and we have this result. Run again and run again, and we have these results. And visualization of logistic distribution. Comment this plt.show sns.distplot random. So copy this and we have just have size and set is to false. Run, and we have this visualization. And difference between logistic and normal distribution. Both distributions are near identical, but logistic distribution has more area under the tails, meaning it represents more possibility of occurrence of an event further away from mean. For higher value of scale or standard deviation, the normal and logistic distributions are near identical apart from the peak. So copy and paste, set label to logistic and random dot normal, size is 100, scale is 2, and label is normal. Run, and we have this visualization. For example, run again, and yep. Hey guys, in this part we talk about multinomial distribution. Multinomial distribution is a generalization of binomial distribution. It describes outcomes of multinomial scenarios, unlike binomial where scenarios must be only one of two. For example, plot blood type of a population or dice roll outcome. It has three parameters: n as number of possible outcomes, for example 6 for dice roll. P-vals is a list of probabilities of outcomes, for example this 1 of 6, 6 and 1, 2, 3, 4, 5 and this, for example this for dice roll, and size is the shape of the returned array. So draw out a sample for dice rolls from NumPy import random and print random dot multinomial n is 6 and p-vals is a list, and so copy these and paste here, uncomment, cut, and 1, 2, 3, 4, 5 and 6. Run, and we have these dice rolls. And note, multinomial samples will not produce a single value. They will produce one value for each p-val. And note, as they are generalization of binomial distribution, their visual representation and similarity of normal distribution is the same as that of multiple binomial distributions. Hey guys, in this part we talk about exponential distribution. Exponential distribution is used for describing time till next event, for example failure and success and etc. And it has two parameters: a scale as inverse of rates, CLAM in Poisson distribution and defaults to 1, and size is the shape of the returned array. So draw out a sample for exponential distribution with 2 scale and with 2x3 size. So import random and import matplotlib and cborn. So print random dot exponential, the scale is 2, size is 2 and 3. Run, and we have these results. And visualization. So comment SNS dot listplot paste, size is 1000 and remove the scale. Paste is false. Run, plc dot show and run, and we have this visualization. And relation between Poisson and exponential distribution. Poisson distribution deals with numbers of occurrences of an event in a time period, whereas exponential distribution deals with the time between these events. Hey guys, in this part we talk about chi-square distribution. Chi-square distribution is used as a basic to verify the hypothesis. It has two parameters: df as degree of freedom and size. So draw out a sample for chi-square distribution with degree of freedom 2 with 2 by 3 size. Print random dot chi-square, df is 2, size is 2 and 3, and equal sign. Run, and we have these results and visualization. So SNS dot list plot, copy, and size is 1000, set is to false. Run, and we have this visualization. Hey guys, in this part we talk about Rayleigh distribution. Rayleigh distribution is used in signal processing. It has two parameters, scale as a standard deviation. This decides how flat the distribution and will be default 1. Size and size. So, example, draw out a sample for Rayleigh distribution with a scale of 2 with size 2 by 3. Print random dot Rayleigh, scale is 2 and size is 2 and 3. Sorry. Run, and we have these results, and run again, and yep. And visualization of Rayleigh distribution. SNS dot list plot random. So copy this and change size, remove the scale, and hist is false. PLT dot show. Run, and we have this visualization. And similarity between Rayleigh and chi-square distribution. At unit STT and 2 degrees of freedom, Rayleigh and chi-square represent the same distributions. Hey guys, in this part we talk about Pareto distribution. Pareto distribution, a distribution following Pareto's law. For example, 80-20 distribution. 20% factors cause 80% outcome. It has two parameters, A as shape parameter and size. So, draw out a sample for Pareto distribution with shape of 2 with 2 by 3 size. Print random dot Pareto, A is 2 and size is 2 and 3. Save and run, and we have these results and visualization. So PLT dot show in here, and SNS dot list plot, copy this and change size to 1000 and set KDE is false. Run, and we have this visualization. Hey guys, in this part we talk about Zipf distribution. Zipf distribution are used to sample data based on Zipf's law. Zipf's law is a collection. The nth common term is 1/nth times of the most common term. For example, the fifth most common word in English occurs nearly one fifth times as often as the most common word. So it has two parameters, a as distribution parameter and size. So draw out a sample for Zipf distribution with distribution parameter 2 with size 2 by 3. Print random.zip and a is 2 and size is 2 and 3. Run and run, and we have these values. And visualization of Zipf distribution. So sample 1000 points, but plotting only ones with value less than 10 for more meaningful charts. In here, so set x to comment and copy, change the size to 1000, and sns.listPlot x and x less than 10, KDE is false, and plt.show. Run, and we have this result.